sec. Yes, I'm now recording.
Alright, today I'm going to be doing a British tutorial on the applications we have seen in our calc group of the Schwarzian derivative. However you wish to pronounce that. Ignore the August 1st, of course, because it's not August 1st, unless you're a time traveler. Anyways, slide number 1. What we want to show today is that pardon me while I think. What we want to show is that the Schwarzian derivative of a composition of functions is equal to the Schwarzian of the former composed with the latter function times the latter function's first derivative squared plus the Schwarzian of the latter function. Saying former and latter, it's probably not, it'll work for now. And we can see here the definition of the Schwarzian derivative. Let that sink in. Shall I continue?
Yeah, good for me.
All right. So, our proof begins by finding the first, second, and third derivatives of our function, which I've calculated ahead of time and will not go over. Said algebra will be left as an exercise. On the line, you see that the first derivative is going to be just by the chain rule that you can read fine, I believe. This is just by the chain rule, and we've gone over this plenty of time. And by taking what we see there and taking the derivative of that, we apply both the product rule and the chain rule to get what we see in the second derivative, which would be this. I can't quite, what's the proper name? Highlight stuff. Actually, can I? Oh, that works. Now, how do I undo that? That would be the second derivative, as you can tell by the two prime marks. Don't know why I said prime. And our third derivative is just the second derivative, except we apply the, I don't believe that there is a named rule for the addition of something within a derivative, but we can break this into two separate derivatives.
I think linearity is the word you want, right?
Yeah. We apply the product rule and then chain rule for each one of these. Their own. To finally get this lovely and incredibly long boy. We can now continue with our known definitions. We're going to insert this into the Schwarzian, and it's going to get very ugly, as you can see by the multiple lines. You can see, wow, this highlighter is actually really useful. So what we're going to be acting on is what we have inserted here. We're going to be using FOIL on it, and once again, I can't quite remember if there's a named rule for how this applies to fractions, but you can see the result of squaring this down here. It's ugly, but it works. Yeah. And after this, is there any questions, of course?
No, I'm happy so far.
All right. Next up, we're going to be distributing this negative 3 over 2. And here's where I stop putting down titles. All right, we're going to distribute this negative 3 over 2 and quickly comment here that we see that this middle term has a 2 in front. So that is going to undo this 2 here, and in the next one we are going to see that this becomes a 3. I believe that is clear enough.
Makes sense, yeah.
We see how it is true algebraically. Just, oh god. I'm relying a bit too heavily on this highlighter, but it looks really nice. We see that these two highlighted terms will cancel, because, well, they cancel. That's quite a way to word it, and as a result of those two canceling, we're going to have this chopped off equation here,
Oh no.
there should be, to my knowledge, oh god, no, this is going terribly. On top of this lower equation, we're going to have on the right side, we lost a parentheses squared. Just making sure that's clear. Is there any further questions?
No, that makes sense.
All right. Asking more questions, make sure that helps for it to go longer. Yes. We can see by factoring out a g prime, yes, g prime squared from the first and fourth terms, which I shall go back and look at. Help. And it would be clearer if the square was still there, but I believe that you understand what is. I done. Yeah, I'm thinking weird. I meant to point out this one. That's sufficiently clear. So we're going to be factoring out the g prime squared of the first term and the third term. Why did I write it that way? Good job, yourself. Anyways, we can factor that out and get the equation, the upper equation seen here. But working backward from the definition of the Schwarzian derivative, we see that this is equal to the Schwarzian derivative of f on its own, composed with g, since g is on the inside of each occurrence here, etc. And this is all times g prime squared. And we see that this entire area over here is also equal to a Schwarzian derivative, except of g this time, composed with nothing. Is there any questions?
Good, yeah, so the derivation makes sense. Let me ask you to think on your feet a little bit and apply this to an interesting case where this is important. So suppose I give you a function f, and I tell you that the Schwarzian derivative of f is negative. So for any value of x, I take the Schwarzian of f, and it's going to be a negative number at the point x, regardless of what x is. And then I ask you the question, suppose I take the Schwarzian derivative of iterated applications of f. So for instance, f of x, or f of x, and so on. F iterated or composed, I don't know, n times or something, applied to x. So if you look at your equation for the Schwarzian of a composition of functions, could you explain to me how you would decide what the sign, positive, negative, or 0, is going to be for the Schwarzian of this iterated function, which is applied like f n times f of x, and so forth. Could you decide what the sign of that is going to be if I tell you that the Schwarzian of f itself is negative?
Thinking.
Well, maybe we should think about the first one. So the first one, since we're composing f over and over, the first case is f composed with f once, so f of x. So
Yes.
what does your equation 1 look like for f of x, in particular when f equals g?
Are you simply suggesting substituting g for f, or is there further work to be done there?
Yeah, for this question, just tell me what that equation 1 looks like when g equals f.
Well, when I guess guess I could just talk it out. Our equation 1, where the Schwarzian of f composed with f, that is going to be equal to the Schwarzian of f composed with g, Schwarzian of f composed with f times f prime squared plus Schwarzian of f.
Okay, so if I've told you that the Schwarzian of f, which is script df, if I've told you that script df is negative for every single input, can you tell me what the sign of the right-hand side of equation 1 is going to be then?
I believe it is eternally going to be a negative.
Good. Walk me through how you came to that conclusion.
That is a statement, because I don't know how I came to that conclusion. It just seems right. But that's not enough. It seems like even if the first derivative of f squared means it's always going to be positive.
Right, so that's a positive number, but the positive number is multiplying the Schwarzian of f evaluated at a particular point, say f of x, right? And I've told you the Schwarzian is always negative, right? So what does that tell us?
So that means that we're going to have that a negative times positive plus a negative. So this is negative plus a negative, and therefore will always be negative.
Good, yeah, so that's true for the first derivative, or the first, the Schwarzian of the first composed function, f of x, right? So if I've told you the Schwarzian of f is always negative, you've told me that now the Schwarzian of f composed with f is also always negative, because it's a negative times a positive plus a negative. And then by induction, that's true for however many times I apply f, right? Because now if I take f of x, then that's f composed with a function whose Schwarzian is always negative, based on what you've just told me. So now the Schwarzian of f of x is also always negative, right? So it sounds like that's true, as you say, eternally. However many times we compose f, its Schwarzian will always be negative.
Is there any further comments or questions? I don't know.
No, that's good. I think you answered that adequately, so I'm happy.
Okay, we can now continue to whatever slide wasn't the last. Now that we have shown that to be true, we can go on to the next problem we are given. We have to show that given a function f equals a of x, ax plus b over cx plus d, where ad minus bc does not equal 0. We have to prove that the Schwarzian derivative of f is equal to 0. Oh, may I quickly comment mid teaching lesson that question for Christian, is this choice of AD minus BC does not equal 0, is this intentionally almost identical to our matrices sessions?
Yes, absolutely. The Schwarzian is very closely related to a certain action of 2x2 matrices. And in that formulation, in terms of matrices, you require that the determinant is not 0. So as you see, the statement that AD minus BC is not 0 is the same as the statement that the determinant of the matrix is not 0, which is really just saying the matrix is invertible, as we've seen. Very good.
Okay, because I was thinking about that for a while, and I'm like, I don't know. We shall continue. Once again, we algebraically, by a combination of the product rule, chain rule, and so on, we have a first, second, and third derivative. Actually, did we at any point state that f can be taken to the third derivative?
So I should have said at the beginning of the problem, assume f is C3, but actually you don't need to assume that because assuming, well, let me ask you, can you prove that if I assume AD minus BC is non-zero, that this function will have 3 derivatives? Can you prove that that's true?
I am inclined to believe that I could, but I could not on the spot.
Okay, that's fine. So, uh, I guess the only points you would be worried about are points where the denominator would blow up, right? So you would worry about
Yes.
points where x is minus, what is it, d over c or something. So you would worry about those points to see whether the function itself has derivatives. So um, yeah, maybe it's hard to do this on the spot. So for now, I think it's safe. Let's just, I mean, you can assume that we ignore those points where x equals minus d over c and say that assume the function has 3 continuous derivatives everywhere.
We shall continue. Once again, this can be solved through, well, the first, second, and third derivatives can be found through a few sheets of paper. More like paper if you actually know what you're doing, unlike me. We can continue now, since we have the first, second, and third, and insert this into the definition of the Schwarzian once again. We see that since division is multiplication by the inverse, that we can effectively swap the places of the cx plus d to various powers across the denominator numerator border to get the equation that we have here. Ah, yes, I forgot I had this thing. Don't know why I need to highlight that. Just first, quick equation 18. We can then cancel the occurrences of AD minus BC across and the occurrences of CX plus D. We see that, well, that works very well. So this is going to result in a CX plus D squared on the bottom, as we can see here, just by the rules of divide. Oh, yes, the power rule of division. And identically, we have these two boys that will simply, I don't know why I keep saying boys, it's too tempting. We see here that that is going to divide out and identically, except without having to deal with power rules this time. I don't have to highlight it. The AD minus BC is going to divide out. And we know that we can do this because we state, well, it was stated in the hypothesis that AD minus BC does not equal 0. Now, continuing on, we can see, and get rid of that highlighting quick. Okay. So, thinking about how to properly word this. So taking the square of what we have here, that works well enough. That is going to result in a, to my knowledge, negative 4c over some junk. Oh wait, just, yeah, cx plus d squared. We don't need to FOIL. And we can distribute the negative 3 over 2 to the top and bottom to get out on the top that it is equal to 6, excuse me, yes, 6c squared over cx plus d squared. And that zeroes out relative to our left element here and we get 0. Is there any questions?
Well, I was going to ask about where we use the assumption that AD minus BC is non-zero, but you explained that very clearly. Yeah, in line 18, clearly we would have a 0 divided by 0 if AD minus BC equals 0, so good. I think you handled that pretty well. So I will attempt to make up a different question on the spot, which is the following. Uh, let's think about the units of the Schwarzian derivative. By units, I mean actually physical measurements. So if, say, f of x is a function which has, I don't know, maybe f has units of, I don't know, meters or something, and x, the input variable, has units of seconds. So maybe the function f of x tells you how far you've traveled in a particular direction as a function of time. So the output f has units again of meters, which are distance, and the input x has units of seconds, which measures time. Can you tell me, either using this slide or the definition of the Schwarzian, what are the units of the Schwarzian derivative of f?
Hmm. You're probably hearing like paper crinkling over here.
I just heard you go, and I heard nothing else.
Okay, so it's not that sensitive. Good.
Good. Well, an easier question first. So,
I'm inclined to believe that it may be unitless.
why is that?
I don't know.
Okay, well, let's go back to the slide with the definition, and then I'll ask an easier question first. So, if f has units of meters and x has units of seconds, first, what are the units of f prime, the derivative of f with respect to x?
Would that be meters per second?
Good, but tell me why.
Hmm. Okay. Let's get some more fun.
Well, what's the definition of f prime in terms of a limit?
The straight up definition of the derivative, are you asking?
Yes.
This would be the limit as h goes to 0 of. I got that in the wrong order, but you know what I'm talking about. The limit of h as h goes to 0 of f of x plus h minus f of x all over h.
Good. Okay, so taking the limit as h goes to 0 can't change the units, so what are the units of the top and bottom of the fraction you just told me?
It would seem that on both. Okay. So on the top we have units of meters, and on the bottom we have seconds.
Good, so that sounds a lot like meters per second,
Cool.
which was the answer you gave, but now we actually proved it. Okay, so good. F has units of meters, x has units of seconds. As you say, f prime, the first derivative of f with respect to x, has units of meters per second. Great. All right, so what are the units of f double prime, the second derivative?
All right. Let me think about this some more. We could simply reinsert this into our definition of derivative, except with f prime instead of f. So it seems that we have This is weird. It would seem that on the top we are going to have meters per second over seconds.
Good. So simplify that.
Just meters.
So meters per second should be meters per
Oh
second
my
squared.
god, meters per
Right.
second squared. Why did I?
Good.
Nice job, so. Okay.
So I think we can guess the pattern now, right? So F
Yeah.
has units of meters, F prime has meters per second, F double prime has meters per second squared. So if we assume F is C infinity, so I can take as many derivatives as I want, what are the units of Fk? So the kth derivative of F with respect to X.
Um.
Berna realizes you were too busy to chill.
Oh my. I have no idea what that icon is, but I love it. Going to be meters per second to the power of k.
Okay, good. I'll try to wrap this up so you can go talk to other humans. Okay, so good. So we know the first derivative is meters per second. The second derivative is meters per second squared. The third derivative is meters per second cubed, and so on. So with that knowledge, can you now look at the right side of equation 2 and simplify all of those fractions to tell me what the units of the Schwarzian derivative of f should be?
So we have that f triple prime is going to be meters per second cubed, and on the bottom you're going to have meters per second.
Good.
So overall there we're going to have meters per second squared, and on the right side we're going to have, thinking again.
Well, hold on. Go back to that last step. So if you divide meters per second cubed by meters per second, that's the same as multiplying by the inverse, right? So that's meters per second
Correct.
cubed times seconds per meter. Meters cancel. And what's that result
Oh,
in?
thinking. Yes, I forgot. So that is going to be still thinking.
So it's seconds per seconds cubed, right?
Yeah,
What happens when you simplify seconds per seconds cubed?
seconds.
I think it should be 1 over seconds squared, right?
What?
So seconds per seconds
Oh my
cubed.
god.
It's just algebra, right? It's s over s to the power 3, which is s to the power 1 minus 3, which is s to the power minus 2, right? So that's 1 over seconds squared.
Makes sense.
Good. Okay, second term. F double prime over f prime squared.
So this is going to be meters per second squared over meters per second.
Right, all squared. Good.
Algebraically identically, meters per second over meters per second squared, or 1 over second?
Yeah,
1 over...
1 over second, and the whole thing is squared, right?
Yes.
Good.
So that means... let's see. I've already forgotten what our units of the right side were. That was 1 over the second squared.
Yes, so the first term is 1 over second squared, and as you've just told me, inside the parentheses, we have units of 1 over seconds, but the whole thing is squared. So we're in good shape because we're adding, or really subtracting, we're adding or subtracting two terms with the same units, 1 over second squared, which is good. So actually, that argument you've just worked through applies regardless of what the units of f are, because you'll notice we have 1f in the numerator and 1f in the denominator for both terms. So the units of f cancel regardless of what they are, and we're left with the units of x raised to the power minus 2. Right, so if x has units of seconds, it's 1 over second squared. If x has units of something else, I don't know, joules or coulombs or whatever, it will be 1 over that unit squared. And the way to see that very easily is to just look at equation 2 and count the number of primes upstairs and downstairs in each factor, right? So the number of primes is going to give you the number of units of inverse x, right? So in the first term we have 3 primes upstairs, 2 primes downstairs, 3 minus 1, or sorry, 3 primes upstairs, 1 prime downstairs. 3 minus 1 is 2. So we have 2 powers of the inverse units of x. And in the second term we have, well, the square of 2 primes upstairs and 1 prime downstairs. So that's the square of 1 prime upstairs, which is 2 primes upstairs. And again, that's going to be the units of x raised to the power minus 2. Good. So that's a very common argument in physics and other physical sciences, is counting the number of powers of various units appearing in terms in your equation. So good. I mean, your answer is correct. I'm just expositing why this is useful.
May I ask, when would you use meters per second?
Meters per second cubed are the units of a quantity called jerk. I don't know if you've heard of jerk. You can go on Wikipedia, but jerk is the time derivative of the acceleration of a particle. So jerk appears occasionally in introductory physics classes. You normally deal with velocity and acceleration. The derivative of acceleration is jerk. This is mostly interesting, I think. You're Googling now. Yeah. Wikipedia is going to have a lot to say about this.
Yes.
Yeah.
Jerk physics. Oh. Okay.
Yeah, so jerk has units of meters per second cubed is the point.
Okay.
But, yes. It's kind of a contrived example, but that's one.